The objective of this demonstration is to implement RK-2 method on the problem of y prime equals y minus t squared plus 1, where the initial condition is specified as y of 0 equals 0.5. And we have the analytical solution with which we will compare the our calculation, our numerical calculations. And RK2 strategy comes with the two K calculations, K1 and K2. So here I'm going to implement it. At first, I define the time, and then y, the values of y, and I call it numerical values. Well, I require K calculations. So I first write here K1, then I write here K2, and then the numerical calculation of y. And I will compare these values with the exact or analytical one, and I will also compute the errors. So the time starts at 0. We have no K values, and the numerical value at t equal to 0, it is the initial condition. So numerical value of y is available 0.5. This is initial condition. This is special one. So I highlighted that it is initial condition. Now with some step size, so let's define a step size of say 0.1. So we can generate a time vector. This is something that we do in the programming. We define the time vector. So it's all up to you how much domain of time you define. Now I can access to the analytical solution, but let's delay it for the numerical calculations. Now the first calculations begin with the calculation of K1. Now the expressions written in Microsoft Excel, they are like the expression you write on your calculator. So I have to write like the expression for dy. So every time when I refer to f of ty, it means this expression, y minus t squared plus 1. So first calculation K1. K1 calculation is h times f of ti by I, which means I have to multiply h with this expression evaluated at ti by I. So I write here h, which is 0.1 times f of ti by I, so which is y minus t squared plus 1. So y here is this value, y minus t squared. So t value, ti value, right? So ti value was the previous value of time, and I have to square it plus 1. In the programming language, you can provide just here f of ti by I, right? But on calculators, you have to use the exact function. So K1 has been computed. Now for K2, I have to compute h times f of ti plus h by 2. So every t in the expression, every t in f of ty will be replaced by ti plus h by 2. And every y in the expression of f of ty will be replaced by yi plus k1 by 2. So this is a careful calculation. So I write here h, which is 0.1, h times f of ti plus h by 2 yi plus k1 by 2. So I have y. So y must be replaced by y plus k1 by 2. So k1 by 2. So this is y from the function. minus t squared. So t value, ti value, ti plus h by 2. So ti plus h by 2 and square of it. So t has been replaced by ti plus h by 2, right? Plus 1. And I have completed the parentheses, right? So this is the expression to compute K2 with respect to this problem, right? So every y was replaced by yi plus k1 by 2 value, and every t in the expression was replaced by ti plus h by 2. So that is the calculation of K2, right? So this step has to be done very, very carefully. And you have to take the proper protocol of the parentheses. And after that, yi plus 1 will be equal to the old value of y plus the K2 value. And that's it. So this is one step calculation. And then for the rest of the calculations, the numerical method will take on. And we can perform this calculation in a repeated fashion. So first K1 will be computed, then K2 will be computed, and then the Y calculation will be performed. That is the algorithm, right? Which is analogous to the Euler's method. The Euler's method was the fundamental one. And now let's compare it with the exact answer. So we have the expression for that. So exact expression is t plus 1 squared. So I say the current value of t plus 1 and square of it, square minus 0.5 times e raised to the power t. So value of t has been taken from A3 cell. So first value is exactly the same. Okay, so RK-2 method, whose accuracy is equivalent to Taylor's method of order 2. So error computation, numerical value minus the reference value. In this problem, we have this reference value from the exact expression. So this is the error, right? One way of defining the error. So let's see. Okay. So the answers are accurate up to 3 decimal places, right? So similarly, in RK4 calculations, you have to have the 2 more K calculations. And that method is accurate up to Taylor's method of order 4. So that is the demonstration for how do we calculate the RK2 calculations with the help of a calculator. So you have to evaluate the expression very, very carefully. But if you do it on a programming language, then the function definition will take care of everything, right?